I want to talk about partitions of n-valued maps, and my cute title is A Meal in 4 Courses. So this is a continuation of work that started in this paper that I mentioned with Bob and Charlotte and Carol. Published in 2020, although we did the work several years ago before that. And what I'm going to talk about was stuff that I was working on around that same time, sort of on the side from this paper, and then I put it aside to wait until this paper was done, and then I kind of lost track of this stuff until the past couple months. I sort of dug out this old paper that I wrote that was almost done at the time, and I finally got around to finishing it off. Anyway, this is about n-valued maps. So an n-valued map, what that means is a continuous function, x to x. It doesn't actually have to be x to x. Most of the talk I'm going to talk about x to y. That's a typo. Where the number of points in the image equals n for each x. Sorry, this is two typos on the first page. This n here should be at x. Sorry about that. The number of points in the image is just the same for every point in the domain. All right, that's called an n-valued map. Every one point goes to n different points when you do the function. And the typical example that you should imagine is the square root function, which is two-valued. Every number has a positive square root and a negative square root. It's two-valued apart from the 0. You got to disregard the point 0. But I'm going to view the square root on the complex plane. Apart from 0, it is a two-valued function because every number has two square roots. By the way, I would encourage you to interrupt me. Just shout out. I probably won't see if you push the raise your hand button or something. Two-valued function, the square root is. All right. I would like to just look at such functions for now on the unit circle. So you could consider the unit circle inside the complex plane, or the unit circle, consider that as like the interval with the two endpoints identified. And if you consider it in that way, the square root function is the same as this two-valued function right here on the interval. So the values I'm plugging in for t are just from 0 to 1. And I say mod 1, meaning if these values ever exceed 1, you just wrap them around back to 0. All right. And you can graph this function like that. This function has two y values for every x value. So this is a two-valued map. This special one, this is called the linear, for obvious reasons, the linear two-valued map on the circle. All right. And in general, we can consider a linear map of some other degree on the circle. So this one here would be a linear map of degree 1 with two values. In general, you could consider the linear n-valued map of degree d by a formula like this. It looks like sort of straight lines with slope d over n that are offset in order to kind of fill out that square in the way that you just saw. All right. If you're thinking about in the complex plane, this is something like the power map of z to the power d over n. So for example, the three-valued map of degree 4 looks like this. These are all lines of slope 4/3, right? And these linear maps actually give a complete characterization up to homotopy. That is, here's the theorem that Bob demonstrated in 2006. Any n-valued map of the circle is homotopic to the linear n-valued map of some degree d. Homotopic just means you can, if it's not quite linear, you can sort of straighten it out by a continuous motion of the graph. You could think of it that way. No matter what you start with on the circle, all of them are homotopic to one of these linear n-valued maps. That's Bob's theorem. Now, what I want to focus on is there's a question concerning splitting an n-valued map. If you have a function where there are n y values for every x value, is any such map just a collection of n different single-valued maps just taken together, rather than one map with n different values? Isn't that just the same as n different ordinary single-valued functions just taken together? Here's an example. This is the 4-valued map of degree 2. It looks like that. And if you look closely at those lines, I'm going to color them in. And I color them in a way such that the colors sort of wrap around appropriately, because remember, we're imagining this, the x-axis represents the interval with the two ends glued together. And so these lines, they need to match up. When you go off the right-hand side, it should come back on the left side at the same point. And so what you see here actually is, in this example, this 4-valued map actually does consist of 4 individual single-valued maps that are all just kind of stacked next to each other. And they are the 4 different colored lines there. All right. So in this case, we say this 4-valued map is called split. It means it splits up into 4 single-valued maps. Right. But this doesn't always happen. So this old example, the square root here, this does not split into 2 single-valued functions. It looks like those are 2 lines, but those lines individually don't make real functions. All right. For instance, the one on the bottom there is not a function on the circle because the 2 endpoints, if you look on the left side and the right side, they don't actually match up. If you were only looking at the line segment on the bottom, the value when you plug in x equals 0 is different from the value when you plug in x equal 1, and so that's not a continuous function on the interval with the 2 endpoints glued together. It only becomes continuous if you take both of those segments at once. Then it is a continuous 2-valued function. All right. So this one is not what they call split. Split means you can break it up into a bunch of single-valued functions. You cannot in this example. All right. So here's the definition of split. It just means that if f can always be written as a set of points that are the outputs of n different functions, then you say f is split. All right. And here's the theorem. This is from a paper by Helga Schirmer, who really did a lot of the groundwork for the theory of n-valued functions, at least as it pertains to topological fixed point theory, which is sort of my angle on this. If the domain is simply connected and you have an n-valued function, then it is automatically split. So this is a really important theorem in the development of the fixed point theory for n-valued maps. It says if your domain is simply connected, then everything is split. Simply connected means there's no holes in the space, so the circle is not simply connected, which is why there are some examples on the circle which do not split. But if it is simply connected, automatically splits. And another theorem, this is Bob showed this in his paper that I mentioned before. On the circle, it's easy to tell if it's split or not based on the degree. Like I said before, if n divides d, then it's split. Well, it's split if and only if n divides d. So that's a nice characterization. All right. So what I want to talk about is what I call partitions of n-valued maps. I would like to consider the more general idea of splitting a multi-valued function into some amount of pieces, but those pieces, they can still be multi-valued. So we are not trying to split it into a bunch of single-valued functions, but just split it into some number of other multi-valued functions. So, and I'm going to call this a partition of an n-valued map into k pieces where perhaps k is less than or equal to n. If k equals n, then that's a splitting, like I said before. But maybe you can split it up into fewer pieces. All right. For example, the 4-valued map of degree 6, if you graph that, it looks like this. And I have colored the pieces in such a way that if you look carefully, you'll see there are 2 pieces, the red piece and the black piece. But the red piece itself and the black piece cannot be broken down further into more sort of finer pieces. So this one is not split. It doesn't break into single-valued functions, but it does have a partition into 2 pieces, each of which are 2-valued. And these each have degree 3. So this is the kind of thing that I want to talk about. Partitions of n-valued maps. This is the name of the paper. I would like to present, you know, my cute title was A Meal in 4 Courses, so I'm going to give you 4 equivalent conditions that, that you can use to determine if there is a partition or not for your function. On the circle, it's fairly straightforward to work out in a lot of detail, although in more general spaces, there are more general results. So 4 equivalent conditions. And these are, each of them is a generalization of conditions which already exist in the literature for splittings. All right. So the first course, this actually is not new to me, but the first course concerns components, connected components of the graph. And if you were following my pictures so far, this is how I was encouraging you to think about partitions on the graph. For instance, this one here, there's the red piece and the black piece. They are individually two pieces, and the red piece doesn't look especially connected, but you have to remember that the two ends horizontally and vertically of this picture are being glued together. So the red piece does make one connected thing, and the black piece makes one connected thing. All right. So this is just a definition of the graph of f. Everybody knows the graph of a function. This is the same thing, only for a multi-valued function you have to say it a little bit differently, but you can always indicate the graph of a function. And the theorem is f has a partition into k maps if and only if this graph has k different connected components. Like the black and the red indicate that that function can be partitioned into two pieces. All right? And this is a fairly intuitive thing that anybody would have come up with, I think. And in fact, I didn't come up with this. This was done in a paper of Bob's. I actually, when I first started looking at this, I wrote an email to Bob and I said, I've been thinking about, something like splitting a function but not all the way down into single valued. And I said, do you know anything about this? And he said, no, I don't think anybody did that. And then a little while later, he wrote back and he said, actually, I did see one result about this in a paper, and it was his own paper that he found. And so, yeah, this is Bob's result from that paper. All right, that was the first course. Second course concerns configurations. So there's something called a configuration space. If you start with any space y, by the way, when I say space, generally I mean metric space, although some of these things can hold in more generality than that, but everything that I say is true of metric spaces. Some of the things are true more generally than that. But anyway, the unordered configuration space of n points, I'm going to write dn of y, and what this is it is the set of all collections of n different points in y. All right, this is called the unordered configuration space. It is the set of all different ways you could choose n different points. They have to be distinct n different points. All right, and it should make sense, I hope. Any n-valued map from x into y is the same as just a single valued map from x into this unordered configuration space. So it's usually more convenient to talk about this map on the unordered configuration space just because it's a single valued map, and you can say all the usual stuff you say about functions without worrying about multi-values. So from now on, I'm never going to write this f is a multi-function. I'm just going to say f goes from x into the configuration space of n points. All right, they are equivalent. You can also talk about this set is called the ordered configuration space. This is the same idea, only in this case you don't choose just any sets of endpoints, but you choose tuples of endpoints where you pay attention to the ordering of them. That's why this is called the ordered configuration space. And this thing naturally lives inside the Cartesian product y to the power n, because it's just a bunch of coordinates from y. There are n of them. All right, this is called the ordered configuration space. And I said before, a map from x into dn of y, that is just an n-valued map. What if you had a map from x into fn of y? This would be something like an n-valued map, but you always pay attention to the order in which the y values appear in those sets of n points each. All right. In fact, if you had such a function, if you had a map x into the ordered configuration space, you can always break it into n coordinates in this way, because there will always be like some well-defined first value, and there's always some second value, and you can put them in order. And so automatically, in that case, you can split up the multifunction f into its individual n different values, and there are n different functions which make them. So if you have a map into the ordered configuration space, it will always split in the way that we've been talking about so far. All right? So any such map is automatically split. That's what I said. So just to recap what I just said, maps into the unordered configuration space are what we call the nvalued maps. The maps into the ordered configuration space are similar to those, but they automatically split. And the theorem, before I say the theorem, there's an obvious forgetful type function which takes an ordered configuration and just throws away the ordering and considers it as a set. I'll call that P. And this is a theorem by Dassenberg, Gonsalves, and John Gwaski from 2018. A function splits an n-valued map. It splits if and only if there is some other map into the ordered configuration space where the f that you started with is actually this forgetful function applied to the f bar. So the idea is f goes into the unordered configurations, f itself does, but somehow behind the scenes it actually comes from a function into the ordered configurations. That is equivalent to the function splitting, having a splitting. All right. So I want to say something like this, but for partitions. For partitions, it's not too bad. We can consider, instead of ordered configurations or unordered configurations, we can consider something like two-part configurations. So if the n, this is an n-valued map, but you can break the n down into two parts, say k plus l. Then I'm going to define this dkl of y. This is configurations of k different points in one group followed by l different points in a second group, such that none of those points from either group are ever equal to one another. All right. This is called the mixed configuration space. It's like the it's a configuration space where some kind of order is being preserved here. You are separating out the first k from the second bunch of points. But within those two groups, you don't care about the ordering. This is called a mixed configuration space, and I didn't make this up. This is something that people talk about from time to time. And just like before, there is a similar forgetful type function, which takes one of these mixed configurations and just forgets about all the grouping and gives you a totally unordered configuration. All right. And then our theorem about partitions looks like this. If you have an n-valued map, it will partition into two maps if and only if you can do this thing where you get some numbers k plus l, they add up to n, and then f is actually sort of behind the scenes equal to some map into this mixed configuration space, which you apply p to. This is where the word partition kind of seemed appropriate to me, just because this n equals k plus l. That's what that's what we usually call a integer partition. Two numbers which add up to some other number. All right. So this is the characterization of partitioning the function in terms of mixed configuration space. That was the second course of the 4 courses, if you're keeping track of the 4 courses. All right, the third and the fourth courses are based on fundamental groups. This is a topological thing, which I know some of you know quite a bit about, but I'll just review briefly. This is a video here. I figured out how to include a video in my Beamer document. So fundamental group is all about loops in your space. Given some space, you choose a base point, which in this case is that point right in the middle. And you consider all of the loops which start and end at that base point, and we consider 2 loops to be equivalent if they're homotopic. That is to say, you can continuously move one into the other. So here's one loop, here's another loop from the same base point, and those 2 are homotopic because you can move one into the other one smoothly. Whereas here's another loop. This one goes around the hole, and it is not homotopic. Oops, I was trying to... No, we're going to have to watch again. That one which goes around the hole is not homotopic to the other 2 because you can't smoothly pull it and make it look like the other 2. All right, so this is what I'm talking about here. The collection of all such loops with that homotopy equivalence relation on it forms a group, and we call that the fundamental group of the space. And we are going to think of a loop as not quite as one of those sort of on that picture that you saw before, but think of a loop as a moving point which starts and ends at the base point. All right, it goes somewhere, comes back to the base point. That's what a loop is. That's how I'm going to view a loop. All right, and I would like to think about, what if we start with a loop in x, and then we send it across by this function, and it becomes a loop, but when I'm applying an n-valued function to a loop, what's going to happen? A loop, remember, I'm thinking of a single point that kind of makes a journey. When you apply an n-valued function to that, what you expect to see is sort of n different points which make a journey, right, according to the function. So here's something that it might look like. It might look like this. If I had a 3-valued map, it might look like a bunch of, it might look like 3 different loops that these points are doing, right? You'll notice while they're running around there, I don't know how well you can see that, while they're running around the loop here, they're not allowed to touch each other. That's because they have to be 3 separate points at all times. They can't intersect. The points can't collide with each other. All right. Or maybe here's another picture of what this might look like. It might look like 3 points, and they each do a little journey. What's different about this one is that the 3 points in this example that you see here are not going back exactly to where they individually started. They don't have to. All that you really need is the 3 points that you start with. After they make their little trip, you have to get back to the 3 points, but they may not be, you know, each individual point may not go back to where it started. All right. This is what it looks like when you start with a loop in the domain and you send it into a loop in a configuration space. It looks like a few different loops together, right? So every loop in X, the domain, gives you something that looks like that in the codomain dn of y. And in this case, this motion of those points, this one's not animated, but if you think of those points as moving, this indicates a permutation of the 3 base points, right? Each one of them, after these points do their little trip, will end up somewhere else, or it might end up where it started. But that's each such loop will induce a permutation on the 3 base points. In this case, if we order them, you know, 1, 2, 3 from left to right, the point 1 and point 3 are being interchanged by this particular loop, and the one in the middle is staying put because it ends up where it started. All right. So the third course involves this kind of stuff, and I'm going to say this in terms of base point permutations. So if we have a loop in the domain, it induces a natural loop in the a natural permutation in the symmetric group. This is a sigma n, is how I'm writing the symmetric group on n elements, right? It is a permutation of the n different base points in the codomain. Actually, this is a group homomorphism if you do all the details here. And this sigma, what I'm calling sigma, is a very specific kind of simplified form of things that we discussed in detail in this paper with Bob and Carol and Charlotte. This sigma is a group homomorphism. And so sigma, its image as a group homomorphism is a subgroup of the symmetric group, and that means that it gives you an action on the set of, you know, just numbers 1 through n. You should think of every loop in the domain acts on this by permuting the base points according to some rule. All right, and for this one, the action was 1 and 3 are interchanged, and 2 stays where it is, right? It suggests, in the case of this particular loop, it suggests that maybe my function is working according to 2 pieces. There's the one piece which is just doing its own thing for the point in the middle, and then there's another piece which is doing something else for the other 2 points. All right. In this example, this is the other example that I showed you. Here, every point is coming back to where it started, right? So the permutation here will be the trivial permutation, which leaves each of those points fixed. And this, for this particular loop, suggests that maybe your function f is actually working according to 3 separate pieces. All right. And here's the theorem concerning this. Your n-valued map has no non-trivial partition if and only if this action is transitive. What that means is that for every 2 numbers in the set 1 through n, there is some loop so that this this action takes point I to point j, right? So these permutations, they are totally mixing up all the points. They're not leaving one of the points by itself all the time, something like that. All right, this is my third theorem about partitions. Okay, and the fourth course concerns braids. We're going to get some fancier pictures here. Remember, a loop in the configuration space looks something like this, right? This was a loop. What happens when you start with a loop in the domain and then you send it over into the configuration space? You get something that looks like that. Now, this picture is a little misleading. It looks like you have these different parts of the loop. It looks like they're kind of overlapping, but actually these points are not colliding with one another, even though on the picture it looks like the loops are overlapping. Those aren't real intersections of loops with themselves. You can see the paths better if we turn the z-axis into a time coordinate. So here's my fancy animation of that. I'm going to make these 3 points do that same motion, but also make them sort of go downwards at the same time. And it looks like they're about to do it. There they go. Looks like this. So they just did the same motion there, only they went down at the same time. And now this picture really shows you more clearly what's going on with that motion of the 3 points. And this is, oops, I lost it. This is called a braid. This is a mathematical braid. And it is a fact that the fundamental group of a configuration space, if you consider all loops on an unordered configuration space, this is the same as what they call the braid group on that space, the full group of braids on the space Y. This is either a theorem or a definition, depending on your upbringing, how this is presented. All right, this is called the Instrand Braid group on Y. And this is a non-trivial group even when Y is simply connected. So even if the space itself doesn't have any interesting loops in it, you can still get interesting braids. So, but if the space has holes in it, here's what a braid looks like. If you start with something with a hole in it, that's what it looks like just looking at the loops in the configuration space. But as a braid, it looks like this. You can see the strands, they can go around one another, but they can also go around the hole, and that gives you more interesting stuff in the group. And here's another one. This is a cute little Hello Kitty. And here you can see the braids can go around each other, but also around these holes. And so you have a more complicated kind of braid group for these. All right. One thing that you will notice immediately about every braid has what they call an underlying permutation. That is, if you just look at where the 3 points start at the top and you follow them down to the bottom and see where they end up at the bottom, that gives you a permutation of those 3 points. Each one of them ends up somewhere else, or maybe the same place once you get to the bottom. All right. And if the underlying permutation of your braid is trivial, that is, every point starts and ends at the same location at the top and the bottom, then that's called a pure braid. So for example, this one is pure because you can see the blue point starts all the way on the left and ends at the same place. The green one starts in the middle and ends in the middle, and the red one starts on the right and ends on the right. That's called a pure braid. This one, the first one I showed, is not a pure braid because the 2 points on either end are being interchanged by this braid. So that's not a pure braid. In general, this is a thing you can always do with the fundamental group whenever you have a continuous function from one space to another. It gives you for free, you get a homomorphism on the fundamental groups of each space. And in the domain, we have the fundamental group of X, and in the codomain, we have the fundamental group of that configuration space, which is the braid group on Y. And this induced homomorphism is related vaguely to the permutation thing that I talked about before, but the induced homomorphism here actually carries much more information than just about the permutations. Dasseberg and John had this theorem about this induced homomorphism, and they showed that F is split. The original one is split if and only if when you do the induced homomorphism, all the loops that you get are pure braids. All the braids that you get from applying F to loops in the domain, you get a bunch of braids, and every time it's a pure braid. Remember, that means the however many points they are, they end up at the same places that they started at. All right. In such a case, that's equivalent to your function being split. So I want to do a partitions version of this, and it's kind of similar to what we've seen before. Oh, sorry, I meant to say there's a important corollary of this, which I mentioned before was a result of Schirmer. If X is simply connected, then every map will split. That's because if X is simply connected, that is, it has no holes in it, then the fundamental group of X is trivial. And so if you look in the theorem above there, then F of the fundamental group will also be trivial. The only braid you ever get is the trivial braid, which is a pure braid, and so it automatically splits. Anyway, to do the same kind of thing using concerning partitions rather than splittings all the way, I'm going to use this construction. If, again, I can break n into two parts, which add up to n, let B sub KL of Y be the group of braids on Y in which the first K strands start and end in the first K positions, and the other L strands start and end in the other L positions. So I'm not saying every strand ends up where it started, but you can break the strands into two sets which stay where they sort of keep to themselves, each of the two steps. During the braid strand, they might wrap around each other in these two sets, but just according to where they start and where they end. The first K things start and end in the first K positions, and the next L things start and end in the next L positions. All right. This also has a name. This is called a mixed braid group. I actually don't know all that much about braid groups, and I sort of came up with this thing which was needed in order to make my theorem true, and then I went looking for it, and I discovered that, yeah, this is a thing that that has been defined already. This is called a mixed braid group. All right. So this example of a braid from before, this is not a pure braid because some of the strands end up in different places, but it is a mixed braid in B2-1. That is, I can break up the three base points into a set of two things and another set of one thing, where the two things stay to themselves and the one thing stays to itself. All right, so this is a mixed braid. And my theorem about partitions is this: if F has a partition, or F has a partition in two maps, if and only if you can break N into two pieces like that, so that the images of all the loops, they all lie in this mixed braid group, BKL of Y. All right. And I think that'll just about do it. Here's a little summary of the four parts. So the following are equivalent. First of all, non-trivial, F has a partition. I say non-trivial because F just considered by itself, it's like a partition of itself, but that doesn't count. Having a partition is equivalent to the graph is disconnected. That was the first thing. The next thing was about mixed configuration spaces. Then the next thing was about the permutations of the base points, and then the last one was about the mixed braid groups. All right, and I think that'll do it. Here's the references that I mentioned. My paper is just called Partitions of N-Valued Maps. And these videos that I made a few weeks ago over the winter break. I was trying to learn some more animation skills, and I made a YouTube video about braid groups and configuration spaces, which is currently the top result if you search on YouTube for braid group configuration space, which I guess is not much of an achievement, but check it out. I actually did a real world example. I filled a little jar with marbles and shook them around, and if you start the marbles and shake them around and the marbles end up at the same place where they started, then that motion of the marbles actually is equivalent to a braid, which I managed to animate on my computer, and it looks like a bunch of raggedy, tangled up nothing, but I thought it was interesting. All right, I think that'll do it. Are there anybody have any questions?
Yeah, I have a few.
Okay, Bob.
So first of all, just a historical note. You give Helga the credit for the splitting lemma, but actually, after she published, and she had actually attributed it as a special case of something by O'Neill, somebody contacted her and told her that this was actually proved in 1934, believe it or not, by Banach and his student Mazur. So it's actually a very old. They were looking at covering spaces, and it was an entirely different context. But the theorem is there, no question about it. So
Okay,
that's really an old result.
good to know.
One other thing I wanted to mention, I wanted to ask our physicists. I've been told configuration spaces pop up in theoretical physics. Have you ever run across them before, Pierre?
Not in my field, but I do know they do pop up in condensed matter.
In where?
Condensed matter physics.
Okay,
So that's the
matter.
physics of really low temperatures, and then you have behaviors like this, and you get things like braid groups there.
Mm-hmm.
Thank you. Now I'll know where to look for. Anyhow, I thought the video was very cool.
Yeah, thanks. I saw. I was going to mention that configuration spaces and the braid groups are also used in algorithms for like coordinated motion planning of robots. If you have a bunch of little things moving along tracks and you have to rearrange them without them slamming into each other, it is very, naturally looks like the pictures that I was drawing. Or even things like I've seen recently people have started doing like fireworks shows, but with drones, swarms of drones with lights on them and stuff. If you want to plan, you have the drones that are in a circle, and then you want them to rearrange themselves into some other configuration. It's similar types of things that you need to do. Although it's a lot easier in 3 dimensions because the drones, they can move around each other better than if they were confined to a plane or like a graph of lines is much harder for them to rearrange themselves.
Didn't this also come up in automatic automobile parking in parking garages if you have independent? I think you mentioned that. You've got cars in a multi-story car structure.
Yeah, something like that. Yeah.
Self-drive cars, and you want to move them around.
Yeah, I suppose if you had if you had if every car on the road was a self-driving car, they would need to do some fancy planning. Yeah. Any other questions?
So, sorry, Robert, just to add, if you want to look for it, the term you should look is anion.
Anion?
I can type it on the chat, but I think I can only tap to Christopher there.
Oh, really?
Yeah. So it's spelled like A-N-Y-O-N.
Thank you.
That's a quasi-particle that basically it only occurs in 2-dimensional systems, so it's a 2-dimensional quasi-particle, and that's where braid groups happens in physics. I don't really know much about them. I don't work with them.
Thank you.
Great. Well, thank you all for coming. Thanks for your attention.